Okay, in this lesson we are going to be looking at solving for theta, which is kind of like doing inverses on the unit circle. Just so you know, there will be no -1 symbols or no arc symbols in here. So because we're not doing inverses, they don't technically need to be a function. And so we don't need to worry about restricted intervals when we do this. So we will be looking for every single answer on the unit circle, not just the ones in the restricted interval. Okay? So the first ones we're going to look at are ones where we have altered the period of our graph. And I know it's been a while since we've looked at graphs, but um, this is no longer sine at theta, it's sine at 2 theta. Okay, so here's how you're going to handle that. And this is what you're going to do when something is done to your theta right here, and it's not just plain theta. This is what you do. You first of all figure out where sine is 1 on the unit circle. Okay, so this is what I'm going to tell you. Sine, which is your y value. Okay, sine is your y value. So if you think about your unit circle, well, this is the graph of sine 2 theta. So the red line is regular sine theta, and sine 2 theta is the blue line. Okay, so I can see that there's going to be more spots. I can tell by the graph that there's going to be one spot right here where sine 2 theta is 1, and I can see another spot right here where sine 2 theta is 1. And you can kind of go down and figure it out from the graph that it does happen at pi over 4 and 5 pi over 4. Sometimes the graph is a little more difficult for it to happen at. So the first thing I'm going to do is I'm going to figure out where sine is 1. Sine is your y value, and sine is 1 at pi over 2. So what I do is I go over here, and I know that sine is 1 at pi over 2. But that's where sine at theta, I should say, is 1. Okay? This is sine at 2 theta. So what I need to do is I need to set 2 theta equal to pi over 2 plus 2 pi k. Okay, the reason you're putting the 2 pi k down there is because sine's period of the function, it repeats itself every 2 pi. So when I put that 2 in front of my theta, I'm altering my period, and it's going to repeat itself more often than that. So what you need to do now is you need to solve for theta. So I will divide by 2, okay? And then I get theta, pi over 2 cut in half is pi over 4. And then 2 pi over 2 is pi, okay? What that means is that now, since I'm making twice as many periods in the same amount of space, my answer is going to repeat every pi instead of every 2 pi, okay? And what I do is I list your first answer. Your answers need to be between 0 and 2 pi. So obviously pi over 4 is between 0 and 2 pi. Then I'm going to add increments of this number of pi, in this case, to my answer until my answers are bigger than 2 pi, and then I stop. The reason I'm stopping at 2 pi is because 2 pi is one trip around the unit circle, and after that, things will start to repeat itself. So if I take pi over 4 and I add pi to it, I'll do this off to the side. Pi over 4 plus pi, you can get common denominators and make that 4 pi over 4. So pi over 4 plus 4/4 pi would be 5 pi over 4 would be the next answer. Okay, if I take 5 pi over 4 and add pi to it, and again, I'll get common denominators, the next answer would be 9 pi over 4. 9/4 is bigger than 2 pi because 8 pi over 4 is 2 pi, so 9 pi over 4 is bigger than 2 pi. I don't need that answer, and I can stop. Okay, I've hit every spot that that happens for. So that's that one. Okay, similarly here, this is a cosecant one, and with cosecant, it's a little bit trickier. What I'm going to do is I'm going to use reciprocals, and I'm going to change the cosecant to sine. I am not going to change this in here because that's the angle that it happens at, and I'm not changing the angle that it happens at. I'm just using reciprocal functions. And the reciprocal to -2 would be -1/2. Okay? So what I first of all want to do is I want to figure out sine at regular theta is -1/2 at that. Okay, so I'm going to go over to my unit circle. So sine is negative 1/2. Over here, sine is your y value. So your y value is negative 1/2 down here at 7 pi over 6 and at 11 pi over 6. Okay, so I go down here. Sine is negative 1/2 at 7 pi over 6 and 11 pi over 6. But I'm not looking for where sine at regular theta is negative 1/2. I'm wanting to know where sine at 2 theta over 3 is that. So what I do is I do 2 theta over 3 equals negative 1/2 plus, and cosecant also has a normal period of 2 pi. If it were tangent or cotangent right there, you would put pi k because they have a normal period of pi, but sine and cosecant have a period of 2 pi. So I'm going to put 2 pi k. That just means my answers are going to repeat every 2 pi. That's all it means. Then since there's another spot on the unit circle, oops, sorry, I screwed this up. This should not be negative 1/2. This should be 7 pi over 6 plus 2 pi k. Okay, and then I need another one because I have two spots on the unit circle. 2 theta over 3 equals 11 pi over 6 plus 2 pi k. Okay, and now I need to solve for theta. And so what I will do is I will multiply everything by 3/2 to get theta by itself. Okay, 3's cancel, 2's cancel. So I get theta equals 7 pi over 4 plus 3 pi k. Okay, so my first answer that I see right here is 7 pi over 4. That is not bigger than 2 pi because 8 pi over 4 would be bigger than 2 pi. If you add 3 pi to something, clearly it's going to be bigger than 2 pi. Okay, so if I add 3 pi to it, it will be bigger than 2 pi and I don't need to worry about it. Similarly here, I will multiply everything by 3/2. Okay, 3's cancel, 2's cancel, and I get theta equals 11 pi over 4 plus the 2's cancel, 3 pi k. Okay, 11 pi over 4 is already bigger than 2 pi, so I actually don't need that, and I don't need to worry about it. Okay, if we were to look at this function between 0 and 2 pi, and we looked for all the spots where it was -2, the only spot that that happened at right here is at 7 pi over 4. All right, one more of these like this, and then we're going to switch gears a little bit. So I want to divide this guy by 2. So I am looking for where sine at 2 theta minus 70 degrees is equal to 1/2. Okay, so first of all, I'm going to just figure out where sine at regular theta is 1/2. Okay, if you look at your unit circle, sine is your y value. Your y value is 1/2 at pi over 6 and at 5 pi over 6. Okay, so I'm going to go back here at pi over 6 and 5 pi over 6. But this is not regular theta. It's 2 theta minus 70 degrees. So I'm going to go 2 theta minus 70 degrees is pi over 6 plus 2 pi k, because that's how sine works. If it were tangent or cotangent, I would put pi k there. And then 2 theta minus 70 degrees is equal to 5 pi over 6 plus 2 pi k. Now we've got a problem here because we've got some things in degrees and some things in radians, and we need them all in the same units or this is going to get ugly. So I'm going to switch everything to degrees because I think that's just a little bit easier. So 2 theta minus 70 degrees equals pi over 6 is the same thing as 30 degrees. And 2 pi is the same thing as 360 degrees. Okay, over here on the right, if I switch everything to degrees, 5 pi over 6 is the same as 150 degrees, and 2 pi, of course, is still 360. All right, Now I'm going to add 70. I can only add 70 to something that does not have a variable with it. So 30 plus 70 is 100. Divide by 2. And theta will be 50 plus 180k. Okay, so my first answer will be 50 degrees. And then I'm going to add 180 to that. That would be 230 degrees. If I added 180 to that, I would be over 2 pi, which is 360 degrees. I'd be over 360 degrees, so I don't need to worry about that. Okay, on the other side, I'll add 70. And I'll get 2 theta is 220. Okay, divide by 2. 220 divided by 2 is 110 degrees plus 180 degrees. So my first answer is 110 degrees. If I add, oops, 180k, that should be. If I add 180 to that, I will get 290. And if I add 180 to that, I will be over 2 pi or 360 degrees, so I don't need to worry about it. And you can see from the graph that there's a few spots that works at too. Because this actually, I should tell you this. This actually, if I divide by 2, I'm looking for all the spots where sine is 1/2. So you can see that that happens here, and here, and here, and here. So there's 4 spots. Okay. Alrighty. And that is it. That's not it. Here's the next part. Okay, we need to solve for theta. Here, these are just regular thetas, and so they just can be solved. We don't need to worry about the 2 pi k business when it's just regular theta. So I am just going to pretend like this was 4x squared, and I will solve. And I get sine squared equals 1/4. And then I need to square root both sides. When you take a square root like that, you need to have a plus or a minus. The square root of the numerator is 1. The square root of 4, which is the denominator, is 2. So this is telling me to look for every single spot on the unit circle where sine is either positive or negative 1/2. Okay, so positive 1/2 here at pi over 6, and at 5 pi over 6, and negative 1/2 at 7 pi over 6, and at 11 pi over 6. And you can also see from the graphs how that works too. So there's where it's positive 1/2, and here is where it's negative 1/2. Okay, so you can kind of tell that from the graph. So theta could be pi over 6, it could be 5 pi over 6, it could be 7 pi over 6, and it could be 11 pi over 6. All right. And then I just want you to remember some even and odd properties, which we'll talk about here in a minute. And some reciprocal identities are helpful. So you've got those on your formula sheet, and we'll refer to those in a minute. And then, of course, the Pythagorean identities are helpful also. Okay, here I've got an equation that does have all sine values in it. So I'm going to move everything to one side of the equation, one side of the equal sign, I should say. Okay, and then what I want to do, because I need to get sine, I need to just have it solved for sine, I am going to go ahead and factor this. So I will have 2 sine times sine, 1 times 1, and plus and plus. Okay, this is set equal to 0. So of course I'll set each parts of those equal to 0. And then sine in this case will be negative 1/2. And here, sine plus 1 equals 0. So sine will be negative 1. Okay? Now you're going to look on the unit circle for where those happen. So you're going to look for where your sine value, which is your y value, is negative 1/2. So your y value is negative 1/2 at 7 pi over 6 and 11 pi over 6. And then you also need to look for where it is negative 1. And that happens down here at 3 pi over 2. Okay? So sine is negative 1/2 at 7 pi over 6 and 11 pi over 6. And it's negative 1 at 3 pi over 2. All of those answers would count. All right, this one does not, this one has sine and cosine functions in it, and that's going to be a problem. So you need to replace this, okay? And this cosine squared, we can use the Pythagorean identities on and solve that. So I am going to replace that cosine squared with its Pythagorean identity, which would be 1 minus sine squared. Okay. I am going to distribute that 2 through. All right. And then combine my like terms. Okay. And then if I move everything to one side of the equation, I can move the 3 over. So I will have 2 sine squared. I don't know what I was doing there. 2 sine squared theta minus 3 sine theta minus 1. I should be able to factor that also. And so I want to do a negative 2 and a negative 1. Okay? Yeah. All right. Here we go. Sorry, I feel like something's wrong. Anyways, this also you're going to look for where sine is 1/2, and here you'll look for where sine is 1. And sine is 1/2, just so you know, at pi over 6 and at 5 pi over 6. And sine is 1 at pi over 2. All right, I think we've got just 1 or 2 more here. Here you've got, again, 2 different trig functions. I want you to use your identities and replace cosecant squared. So replace cosecant, not cosecant squared. Cosecant can be rewritten as 1 over sine. Okay, so I'm going to go ahead to get rid of that fraction and multiply both sides by sine. And I'll have 5 sine squared equals 4, and then divide by 5, and I will get sine squared equals 4/5. Okay, this is not on your unit circle, so this is kind of a problem. So I first of all need to square root both sides. Okay, and you can just leave it like that. I know technically that has a radical in it, but well, I'll simplify it for you. This is really the square root of 4 over the square root of 5, which is really 2 over root 5, which is really 2 root 5 over 5. Okay, this is still plus or minus. There is no spot on the unit circle where sine is going to be 2 root 5 over 5. Okay, so what you need to do is you need to go to your calculators. Okay, and if your calculator's in degree mode, it'll spit out the answer in degrees. If it's in radian mode, it'll spit out the answer in radians. So you want to put in inverse sine of 2 root 5 over 5. Your calculator will spit out an answer, and then do inverse sine of negative 2 root 5 over 5. Your calculator will spit out an answer. Now, here's the deal. Sine values, this is what happens. When you get a sine value that's in quadrant 1, it can be flipped over the axis to find the same sine value in quadrant 2. So whatever your answer is, to get the other answer, this answer right here, you're going to take 180 minus your previous answer. And then if it's in quadrant 4 down here, you can take 180 plus your previous answer to get the next one. And I don't have a calculator right now, so I'm not going to stick this in, but that's what you do. All right, and then on this one, we are going to move that cosine to the left side so that we can factor that out. Okay, now I have a GCF of cosine that I can pull out of there. And here, cosine is 0. And here, sine is 1/2. So cosine is your x value, and your x value is 0 at pi over 2 and at 3 pi over 2. And your sine value is 1/2, or your y value is 1/2 at pi over 6 and at 5 pi over 6. And I think that that's it. All right, that should do it.